The second part of section 7.4 is surface area. This is for day 66. So we're going to be taking a curve and we're going to rotate it around an axis and create a three-dimensional object. But this time, instead of finding the volume of that three-dimensional object, we're interested in finding the surface area, the exact surface area of that three-dimensional object. So to start, we're going to begin with what's called a frustum, which is a cone that's been truncated. So if I chop the top part off a cone, I'm left with this shaped figure, a frustum. And the formula for the surface area is 2 pi, the average radius, times the edge length L. So the edge length L is here, and the average radius is the top radius and the bottom radius added together and cut in half. So to apply that to a curve, we would take the curve, split it up into lots of little straight line segments, and use those straight line segments as the delta L, or the edge length of our frustum. So to start with the surface area formula, and we're going to have to find the average radius, which is this f of di. Now, the intermediate volume theorem says that there is a radius that represents, there is a y value, that represents the average between the big radius and the small radius. So we're temporarily just going to call that y value f of di. Some sort of d input produces a y value that represents the average radius of this frustum. So 2 pi r, and then delta L is, again, back to the distance formula, delta x squared plus delta y squared. Replacing this with the same trick we had in the arc length formula, 1 plus f prime of c squared delta x by the mean value theorem, we now have a formula for the surface area. That's just for one small frustum. So to get the surface area of the entire three-dimensional figure, which would go from a starting point of here to here, we want the surface area of that whole figure. We're going to add up all the very small surface areas that we find using the one small frustum formula. And again, if I take and make the edge length very close to 0, okay, increase the number of delta L's, but make each one very close to 0, we get the limit process applied, and we get this statement here. So 2 pi antiderivative, radius function, 1 plus f prime of x squared dx. Now the radius function is going to be f of y or f of x, depending on whether you're taking the antiderivative with respect to x or with respect to y. Okay, so let's go into a couple examples. Okay, in example 1, we have the curve y equals 2 root x, and we're going from 4, 4 to 9, 6, which is drawn here in blue. We're going to revolve it around the x-axis, which means our three-dimensional object is this. That point we get rotated around, this point we get rotated around. And so what we're going to do is take this function and substitute it into the arc length formula. So, into the surface area formula. Surface area is 2 pi. The radius, what's the radius? The radius is just the y value. The y value is 2 root x. So 2 root x. The second part of the formula, take your function, take the derivative, square the derivative, and you wind up with x to the negative 1. So it's 1 plus 1 over x. 1 plus the derivative squared produces 1 plus 1 over x. Distributing the root x inside the second square root produces the square root of x plus 1, and the derivative of that is this statement here. Substituting in our x values 4 and 9, we get this quantity for the surface area. Again, that's an exact answer. I don't know that you need to simplify it any further than that. So for the second example, we're back to an arc length question, but this time we have a little bit more crazy function. And what we're going to do is show an example of how to do things with respect to y and not with respect to x. So for this curve, which is plotted here, we want to go from 0, 1 to 2 root 3, 4. 0, 1 is right here, and 2 root 3, 4 is right about there. So we want to find this arc length right here. Solving for x is a little bit easier, so I took this function divided by 9, took the square root, and wound up with this statement. And so now in my arc length formula, I'm going to need the derivative of this squared. So the derivative is y minus 1 to the 1/2. Squaring it, I get y minus 1. And then now my arc length formula, antiderivative from y values, 1 to 4, 1 plus the derivative squared, y minus 1 dy, The ones cancel out. Root y antiderivative is pretty straightforward. We get this statement, plug in my y's of 1 and 4, and I get an arc length of this. So if it looks like an arc length is going to be messy doing things in terms of x, look at the function and see if it's easier to do things in terms of y instead. Okay, that's it for day 66.